Now we have reached the discussion for CFD analysis and the pitfalls and best practices associated with running a CFD analysis. The first group of common mistakes are made in mesh and domain setup. You might have an inadequate mesh refinement in high gradient regions. Boundary layers, points with flow separation, and shock waves require a fine mesh to accurately capture velocity gradients. Your mesh might have poor quality metrics with high element skewness. Large aspect ratios and rapid transition in mesh sizing can cause numerical instability. You might not verify that the results are mesh independent, where the key results don't change by more than 5%, and you might have improper outlet conditions, where the boundary is too close to the region of interest, or there might be backflow on a pressure boundary, or your mass conservation is not addressed across domain boundaries. The best ways to address these errors are with strategic mesh refinement, where you adapt the mesh based on the expected solution gradients, not just the geometry. Your boundary layer inflation should be based on your first cell height, which is calculated for a targeted Y+ treatment. Then you can address flow-specific requirements for stability and solution fidelity. The quality control metrics that you should use when constructing your mesh should be orthogonality of greater than 0.15, skewness of less than 0.8, and aspect ratios that are visually acceptable. You can monitor your cell-to-cell volume change with an acceptable range lower than 20%, and checking for negative volumes and highly warped faces. Most CFD packages these days are quite robust in their quality control of meshes. You should verify that the solution is mesh independent by monitoring solution stability throughout mesh refinements. This should ideally be documented using the verification and validity processes of your company. To address your outlet, place the computational outlet sufficiently far downstream of the true outlet to allow for natural flow exit. Check mass conservation and outlet stability and ensure that the outlet is defined geometrically normal to the flow direction for numerical stability. When addressing physical and numerical modeling, there are mistakes pertaining to unrealistic inlet conditions, where a uniform velocity profile is applied when the true velocity profile is non-uniform. You might have turbulence specifications done incorrectly, meaning your intensity and length scales, or you might have failed to account for secondary flows in the inlet stream. You might not have wall treatment correctly set up, using wall functions that are not valid and not accounting for roughness effects on walls. You might select an inappropriate turbulence model or not validate the turbulence model against similar applications. It is important to note here that the appropriate turbulence model might rely solely on the company best practice, in which case you should consult with your senior or technical leader. Then, there may be some errors in simplification, where you assume steady state for inherently transient problems, like vortex shedding, or you use 2D simplification where secondary flows have a third-dimensional effect, or you neglect compressibility where the Mach number is higher than 0.3. To address the inlet boundary mistakes, you should start simple and add realism. Simulate a simplified inlet that is extended 5 to 10 diameters to allow the flow to develop fully before entering the simulated domain. Your inlet should be defined normal to the flow direction as well. You can add turbulent flow details and velocity profiles as needed. When modeling near-wall flow, you should calculate the first layer height for the correct Y+, based on near-wall flow you expect. Avoid high wall Y+ function in flows with strong separation or reattachment, and always account for wall roughness. When you run simulation, test multiple turbulence models for the given flow regime. You can base your selection on literature or validation cases, but always check your company-specific turbulence model procedures, and then use appropriate physics modeling. Use transient simulations when it's required. Avoid 2D simulation when there are secondary flows and cross-stream motion that are critical, and use compressible solvers when Mach number is greater than 0.3 to capture pressure waves and density variation. When looking at the solution strategy and validation, you might use inadequate multi-phase modeling, maybe making a wrong choice between VOF, Eulerian, and mixture models. You might have insufficient mesh resolution for interface capture between the two phases, and you might have poor specification of phase interaction parameters. You might have poor convergence strategy, where you rely on residuals alone, or you are using inappropriate solver settings, or not allowing sufficient simulation time for the flow to develop to steady state if you're running transient flow. Then you might, less frequently, see over-reliance on high-fidelity models without benchmarking with low-fidelity RANS models first. You might not check that the values make physical sense or match conservation laws. To solve these mistakes, you should follow a structured solution and verification strategy. Progressively model complexity, here specifically for multiphase. Begin with a simple single-phase approximation. Refine the mesh at the interface between the phases, validate the interface interaction terms, and then choose solution models based on the problem's physics. You can use systematic convergence techniques where you first solve first-order schemes and then switch to second-order schemes. You should monitor residuals, mass and momentum imbalance, and have probe locations at critical points to draw data from to compare to your hand calcs. When working in industry, RANS is the most resource-efficient and practically accurate modeling scheme. So these models are used most widely. You should first verify if higher fidelity models are required in your specific industry application and only venture to LES if the project success depends on it. Then finally we get to our results verification checklist. Have a checklist of parameters and results you can check for conservation, trends, and boundary conditions. These might include mass, momentum, energy, boundary condition verification. You might check whether the solved flow matches your expected physical flow, and you can compare your results to analytical solution if those are available.